Welcome everybody to GeoHug. So before we do kick off today's session, I would like to take this time to acknowledge the traditional lands which we're all coming from today. I live on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present, and future. And yes, I am thrilled that we have Mathias Vandelle joining us today. So Mathias has spent over 20 years trekking through the world of mining and geology, from the nickel mines of New Caledonia to the wilds of Madagascar, the rolling hills of the UK, and many corners of Europe. And now the Group Resource Manager for Barrick Gold's Africa operations. He leads a crew of geologists crafting resource models with a keen eye for sustainable practices and endless room for improvement. And with all of his experience, it is going to be brilliant hearing from him today about the golden rules of resource modeling, an internal guide for geologists stepping into the world of estimation. So it's going to be a fantastic session. I hope you all enjoy it. I will be promoting you up as panelists throughout the session. Please don't be shy if you can. Come on through, get the cameras on, get the mics on when we open up for discussion at the end. But yes, thank you so much, Mathias, for joining. It's awesome having you here today.
Thank you, Jessica. Nice to be there.
Very early for you too, so even more thank you.
Yeah, it's a bit dark out there, but it's 7 o'clock in the morning in Spain at the moment, so that's why. So
yeah, we'll
it
just
is
have
what
to
it is.
keep you caffeinated for the next hour or so, and
yeah, I might do that. I might do that indeed.
Awesome. Before we do start on your presentation, I was really curious what got you into mining and geology to begin with.
Well, the science of it, I guess. I actually in when you do studies in France, you study like all the hard science together, including biology and geology. And at some point, the opportunity was there to move towards like a geology engineering school. So I'm a bad geologist. I'm actually like more like a mix between engineer and geo. But anyway, it's and then when in the field, like the mining was like kind of the cool area. So I like that because you could actually open the mountain and see what was inside. So
yeah,
it was a good way to just check. So yeah, anyway, that was the kind of the
starting
reason.
point.
Yeah. And you asked me like to if I had any like rocks to share.
Mm-hmm.
And, well, I explained to you that because we moved a bit around, and when you start moving from one place to another, the first box that doesn't always make it inside the move is the box full of rocks. So I don't have that many yet still, but I got one actually that I really like. This one
face.
Yeah. This rock is, well, it's nothing like very fancy. It's just a rock. It's a ultramafic rock. It's a wheelite that stayed on my desk when I was working in Madagascar for several years, and it was the symbol of what was happening in the mine, because we were mining like nickel laterite there, and we were trying to get rid of like all the big rocks and big boulders. And that one here was actually, I took it from the, like when we were doing some maintenance on the scrubber, and it enters the scrubber as well. The rocks were kind of squarish when they enter, and the fact that it stayed for far too long and ended up being like a nice ostrich egg was actually kind of like a good it was the epitome of the fact that it was a problem, because it would release magnesium into the stream of ore that was sent to the plant, and it would be like it was leading to an overconsumption of acid in the system. So it was costly for us to have like these eggs like lying around. So yeah, it was a good I like that one. And well, also usually people were like, what is that? Is that like natural? No, it's just a reject from the plant. And yeah, so that's the rock I wanted to share today.
That is brilliant. I love that. Cool story too. That's awesome.
All right. Shall we
yeah,
start?
let's get stuck into it. Thank you so much for this.
Before I do start on the slides, I will just talk a bit about like well, the context, and everything I will say downstream or afterwards is it has to be put like, I'm talking here from a place where we are working in a gold and copper production environment. So we do produce and we do models in order to produce. So it obviously like is linked to that. So if people work in academia and in other field doing a PhD, obviously everything I will say might not apply. So that's kind of a small caveat there. But the way we do model is in Africa within the, I'll move that here because this is, how can I do that? All right. Okay. Let me put it on the side. That's way. Okay. So in the African region, when we're doing models, we are actually doing most of the time single model for grade control and resource. We're doing like Matryoshka systems, nested models with different support, different block sizes. And when we have loads of data, we have small support and in some corner of the model, and as the data disappears, then we are dealing with like larger support. So it's something slightly different from what you can see elsewhere. So I was thinking to mention that. And we are also trying, well, not every time, but like the as much as possible, we're trying to run multiple scenarios and to evaluate the what ifs, and not to be too stuck into like, this is the way and this is the SOP of doing a model. We try to be considering like what happens if we do this and what happens if we do that. We have often like an official model, and then we have like what I like to call shadow models that are not released, and models that are just there in the background to be tested and to be, you want to see over time, over 6 months, a year, are they performing the way you want? Do you have the demonstration that actually the change in the model is improving, is helping us production-wise, or is it not? And if it's not, then maybe we should just, keep it inside the box and not release that. In Africa, we are dealing roughly, just for an order of magnitude, with 60 plus deposits and models. That's what we commonly like update and maintain. And we have loads of geos doing that. So it's a collective effort in order to model all of those. And part of my job, just maybe to mention that, is also trying to standardize or make sure that we have like some sort of like similar way of doing things, and that you don't have someone sitting in Congo doing something very different from someone sitting in Zambia, and that we have like a common approach to the way we model things. I'll give you as well an example of Lulu-Gunkoto in Mali. So we do monthly updates of the models. We do one big overhaul once a year for the resource, but otherwise they are like, as data comes in, they are updated monthly. For the five main active mines that we have, that's like 3 underground and 2 open pits in the case of Lulu-Gunkoto mine. And then there is as well like 5 to 10 other deposits that would be updated ad hoc when required. So that's 65 to 70 models being generated every year. So there is a certain speed and rhythm to the release of models, which obviously drives a bit like some of the elements I will talk to afterwards. We tend as well to develop our resource geos internally. We don't, well, we can as well hire like outside, and that, we do that sometimes, but like the best way to have like the people being well trained and like, organized in the way that we want to, is actually to train our own geos. And that's, we have like some sort of a resource academic kind of training stuff that, and like a path where we develop people. And I like doing that. But the good point as well is that we, by moving people to resource after they worked in exploration, in production, in different aspects of the operation, they have also like the background of what is needed downstream, and the relationship that are there to be, developed with the mining engineers and planners, and then process, and like the relationship that needs to go across as that model is used for the production. So the slides I will present afterwards are actually slides I used. They've been pimped a little bit for today. I'll admit that. But the base of it is like slides that been using and that we have been using for quite a while. To take someone who has not done resource before into like what he needs to think, like before running a model. What are the overarching kind of principles that should be there when doing a model? And there will be a bit of discussions on some of the topics, obviously, but it's that's what I will present. So I'll talk to everyone thinking you don't know how to do a model and like take you through some of these slides and trying to, well, time is yeah, it's ticking. I need to move. All right. So first one is a famous one. Box. It's a British statistician, and it's a bunch of quotes, but all models are wrong. We could add to that that some are useful. There is obviously gradation in the wrongness, depending on how much time we spend doing a model. Like, did we just like did we do like a quick and dirty, or did we spend like the last 6 months doing it? Although sometimes it's not like spending the time that will make the model better. It's just like asking the right questions as doing the model. When we do a model, there are different reasons for the models to be wrong. Obviously, the data we collect and a certain number of steps afterwards where we can sometimes leave some, there is room for errors and like misinterpretation and different things. So the main reasons where the models are wrong is, first, we are dealing with uncertainty. So in here, I'm showing like this is data from Kibali in Congo. And there is a scale because I was told that to add some scales. I don't put scales enough on my pictures. But it's the main deposit in Congo, and the color there are just the cluster weights. It's a density kind of measurement of information. So the red areas are like ready to go for mining, and there would be like carpet bombed with information. But so we can actually reduce the uncertainty by adding loads of data when we are actually in operation. However, we can have like an area that is very well informed, and we move like 50 meters away, and all of a sudden the uncertainty level like goes back to level 1, where we don't know, or there could be some things happening there, a fold going on, and something that will just all of a sudden make it like much harder to model. So it's something we need to consider. We don't know what's under our feet, and we need to acquire data, but there will be always like a part of like trying to reduce the best we can the uncertainty. And yeah, that's one key. The second point is, like typically we can say like 1 topic, 2 geos, and 3 opinions. So we are sometimes our own worst enemies, where we like to debate and we like to have different ideas, and we sometimes have, because we are dealing with that uncertainty, we can make different interps. Sometimes it runs some of the mining engineers mad, because when they hear, oh, the geos came up with a new interp, they usually start to shake a bit, because they don't know what's, they like stability in the model. They don't necessarily like big change, because it can have an impact on the downstream in the plan and things like that. Another way to phrase it would be as well, if you ask a geologist what color is a cow, the geologist is likely to answer that it's brown from the side he can see, and for the other side we need to drill. And it's the reality. We are dealing with objects that are not that always easy to catch, and we need some information. We need to gather some info and recognize sometimes that we just don't know. And it's, obviously the resource classification are there to try to picture that and to understand like what do we really know versus, or what do we know the best versus what we do know the least. But it's something to keep in mind. For us as well, and that's something, it's important there. The corollary to that is that the best model is the next model. We are doing like, as I was saying in Mali, we're doing loads of iterations of the model. So like it's okay, you know, if we look back and you look at the model from 2 years ago, it looks a bit like clunky and like not necessarily that smart, but it's just like the best we could do at the time given the data we had. And as time passes, then we are actually improving with the understanding and the knowledge, and the data that we have is improving. We have tested some assumptions, and they turn out to be true or to be wrong, and we corrected the model accordingly. So the best model is the next model. We should not fall in love with one iteration. It's not because, you know, oh yeah, I worked hard, I did that nice model, it's the best. No, it's not. Like the best one is the next one, the one you haven't done yet. And the extension of that is the actually best model ever will be the day you close the mine and the day you're finished, because that's the point in time where the acquisition of knowledge will be kind of at its maximum. The thing as well, when we are modeling things and when we are testing different methods and different approach to the model, is we should try not to be dogmatic. And by that, it means like if we what works in one area of the model or the, you know, like what would fit, for example, the best area of your model and all the decisions that you make in order to model something somewhere, does not always translate very well outside. And it's something that we are dealing with on a daily basis, where we can see sometimes that we made decisions in the past that were based on what we could see at the time, which was probably like the best area of the ore body, like the core, the heart of it. And as we are moving towards outskirts and towards the periphery and towards like the areas around the main, you know, the like more on the periphery of it, then the continuities break down, the grades drop, like it's not that well defined. So it requires sometimes to just step back and reflect and say, well, you know, what worked here is not working there, and the method I'm using, the SOP I defined in order to do that model, is not applicable. I need to investigate what needs to change in order to adapt to what I see now as a reality, and not to be too dogmatic, saying, oh, this is the way and this is the only way to do that. The picture here that popped is from, whoa, it scares a bit, from 15 years ago, almost 15 years ago. It's a trend model. It's a iron on aluminum ratio. So it's a map. It's a map of that chemistry ratio in Madagascar on these. Well, actually, it's my Rocky Mac rock face. It's coming from there. So it's showing like the ultramafic intrusions compared to there are like loads of dikes of gabbros around it. So it shows like a clean map of like the different geological context there. And what we can see is that the red stuff is the ultramafic intrusions. And we can see that what would work on the one in the west it's strongly like iron compared to the others. But we can see that the other two that are more orangey in central and in the southeast are actually, well, slightly different. So what will apply, like the method that needs to apply, or the parameters that need to apply on the western part and the one and the other two, might be different, just because the rocks are different and the context is slightly different. So yeah, I mean, that's something to keep in mind. You want as well to evaluate your models based on, sorry, can I just remove that? Yes, perfect. Okay, thank you. You want as well to be able to evaluate your model. So this is a decluster plot. It plots like the average of composites within the block versus the block estimate. And it's a very nice tool that allows to see like like how the global model behaves against data. So to see how the model is linked to the actually informing data. And even though this model looks a bit smooth, if you apply like some change of support to it, then it will fall into line. So, however, there will be like some areas inside the model that are odd, and you want to investigate, because, well, in here the model is very low, but there is some good data inside. And for those, you want to investigate as well, because well, the data is not that good, but the model is. So there is like some sort of dissonance between the informing data versus what the block says. Obviously, the block model is informed by the neighborhood and not just by the data that is contained inside the block. But still, you can actually check like what is not working in your model and investigate that and fix it in your next model, obviously, or try to fix it or see if you can, like, find a way to improve that. All right. The next one is from, we crossed the Atlantic now. This is an American statistician, Deming. And he said that without data, you're just another person with an opinion. And we do want data. We have to pay for that. It depends on the industry, obviously at the moment in the gold industry or many other operations, paying to acquire data is part of the process. It's not even debated. But there are other parts of the mining world where it's not that obvious. People debate whether or not they need to add like more information. Can't you just find some other way, like play Yoda and just decide, find a way to decipher what is in the ground without paying for it? So but the truth of it is that if you don't measure something, then you can't control it. You need to acquire data to control what's going on inside the model. And obviously, it's not part of the discussion today, or I won't expand on that. But let's say, that's why we have as well all the QA/QC system, because when we acquire data, we want to know, well, is it good data? Is it the stuff that I can trust? Or is it just rubbish because, well, it was taken the wrong way and creating bias left and right? Or is it something that I actually can trust, to inform like the model we want to do or the decisions we want to do? So there was a presentation with you, Jessica, a few months back, if not a year back, I don't know, on ELSAM with Jesse Clark. It was like theorizing the fact that, in order to find like the right modeling practice, you have to look at the lithology, the structural aspects of it, alteration, and the mineralization, obviously, like what's going on there. I have an example here where this one is in Africa, actually, but it's based on the same principles where, you want to define your geological context. We have here like two faults in purple. And after that, you want to understand like what is guiding your mineralization and what is like the likely stream of the mineralizing fluid. Some not always easy to find, but at least you can try. And then eventually you want to use that information in order to guide what would link with what and what grade should talk to which, and in order to understand like what are the likely continuity that would happen in the ground. So that's a concept we apply. There is also like to add on this, there is also like a very multidimensional aspect to a model, because we talk about like, we often talk a lot about like the grade and of the metal that we're trying to model. But like models are actually trying, well, there are like loads of aspects that we should consider and loads of data we should acquire in order to support these multidimensional models. We can talk about oxidation and weathering. In Africa, in gold deposits, this is important because, well, there is quite a significant oxidation profile where the rocks are like destroyed. And it influenced the recovery that we can have and the grade and some of the things like that. So you want to be able to model that. Obviously, in the Canadian Arctic, there is no so much like the supergene weathering is not that much. You're like basically just on the rock. But in different contexts, like tropical Africa, this is one. You want to acquire data and make models about like your geometallurgy and find like, well, how much metal you can recover, or some other aspects of the geometallurgy, because it cannot be always like about recovery. It might be some other deleterious behaviors inside the plant. You want to acquire data on geotech, because if you're mining 1.5 kilometers deep, at some point you want to know if the rocks will hold together. So like, and you can do like a rock mass model and have like all different aspects and variables that you want to measure, and you want to at some point like integrate all of that inside your resource model. Upside, obviously not necessarily the stuff you want to use on a daily basis for your production, but still you want some time to test what could continue. You want to have like some extensions, areas that are like, you know, if you see a shoot and you see a feature that seems to be there, you might want to project that further and then test a few things like, you know, is your open pit like a data constraint or strip constraint? Where do you sit between these two poles? Like, do you have like room for growing a certain, like if you acquire more data and this proves to be true, like do you have like any room for growing your picture or not? And same from underground. So it's good as well to have sometimes like a base case model, and then you can start to play with, okay, I can have like an upside 1, 2, and test what would be the sensitivity of some of the downstream decisions if those end up to being true. You can talk about density. We can talk about density. In the case of density, it's well, we honestly collectively in the industry we don't spend enough effort on like capturing the right densities. At least that's my experience. But it can be actually kind of major. All the measurements we make are usually like massic percent or massic quantities. So like change the mass and the metal change as well. So density can be also start in like complex geological environments plus loads of oxidation. Defining the right density in the right place of your model can start to be a bit complicated. So it requires attention. And the last one is, and that's something that we've been slowly trying to improve and testing, is to talk about dilution models. It's borderline to the resource going into reserves, but you know we are in a production environment, so there is definitely like something that we should talk about. And you want to test, okay, the relationship with like as you mine, you want to simplify the shape that you want to put, you know, that you want to move, because well, we are using big equipments, and or if we need to use like a smaller equipment, we need to know why. But yeah, it's an important aspect of things. There is also like a few things that really fall within the resource guys kind of environment, and something that sometimes we don't like capture. Oh, by the way, sorry. So the ELSAM acronym should like can translate to that. I will let everyone just try in his head to pronounce that. I can't, but it might not be like the best acronym in the world. But you know, we can expand maybe on the ELSAM to have like this. On the other data that we need to consider as well when doing a model, topo, survey, maximum excavation surface, underground as built, it's the kind of data that we need to like really own and understand, because if you want to build good recons, you need to have like good access, a good control over what, you know, what has been mined when, and it's something that is definitely like it's not, sometimes some mines have like surveyors that are really up to the task and they just can deliver anything you ask them, but you should own that. So if you want to understand, like, you know, you should have like your own files and slice and dice them per week, per month, per quarter, per anything you want. And it's an important aspect of data collection that resource geos needs to think of. Same as acid and neutralization potential. It's something that we need to consider. I'll share here just a few ones that like along my career that were a bit like kind of curved balls that I was not expecting. At some point we had to collect some settling velocity. So this is not the typical stuff that you collect. But in that Madagascar operation, we put like the material in, we add water, and at some point we need to remove that water, so we have like thickness, and you expect, you know, starting point was expect like everyone was expecting that, you know, no matter where you are in the orbity, then you would put that water and like, in the thickener, and the particles would just go down. And we unfortunately found out that there were some areas of the orbity where the particles were like some sort of punk teenagers, and they didn't want to go to bed, they didn't want to settle. So you have to find out where they are, what's causing that, and then so that you can. It was a big bottleneck for the operation. If everything just lingers there and floats, then your throughput is down and your production can't operate. Well, can't be there. Redox potential, same thing. Some corner of the plant would just require a certain relationship between different minerals, and it's not necessarily the first thing you do when you collect data at the early exploration stage. So you have to fast track some acquisition of new data or finding proxies. You need to invent something that can help you guide these decisions. Particle shapes, same. Elasticity, you could say hardness as well. Colors, different orbities, different places in the world. Sometimes you get like some sort of like, a bit different measurements that need to be considered. The global idea behind all that rumble is it's just like it requires some strategic thinking. So the way we should approach this is that, okay, what is the data we need? Not now for now. It's like, what is the data we need in 5 years' time? Because if we want to do good recons, if we want to do like proper, like if we want to improve in the future, what is the information that we can collect now over the next 5 years that will be very, very useful to have in 5 years? Or another way to say that would be to say, all right, if I'm thinking about not necessarily myself, but like a geo that will be sitting there looking at the orbity in 20 years, what would be the data I should collect now so that it would be very proud of us for having thought of it, and not being, well, screaming and scratching his face for like the inconsequent people who didn't think of it. So we want data, we want good data, and it needs some thinking on what do we need to get. And sometimes it's like the what ifs, like what if, do we need that? Have we ever measured this? And there are parts of the world where we collect the Mendeleev table now every time we touch a rock, and that's good. But like sometimes there will be additional aspects to the data that needs to be acquired that we might miss. So think about it. The next one is this is different way and different point there. This one is so Ludwig Mies van der Rohe is a German architect. Was one of the founders of the Bauhaus movement, where they tried to build buildings in somewhat like a simple way or simple design. And his quote is "less is more." And that one, well, it can translate into like, if you want to translate that into mining, is like, or in resource modeling, is like, can you with success explain in 2 minutes how the model works to your golden retriever? Or let's say, can you with success explain in 2 minutes how your model works to like a manager? And more often than not, we look like this when we are trying to explain like our models. And the reason for that is because, well, if we try to explain a workflow and the workflow looks like this, then, well, anyone would struggle. And so at some point we need to think about like, what do we want for our model? Do we want just the result? Do we want just like the model that works for us? Like, we just we make a model and it works, and we should not question that. Or should we try to find a way that, should we question the sustainability of the model? Can that model be reproduced by someone else? How much work does it require to that somebody else to reproduce that model? More and more, and nowadays we have like Python scripts, and people are using Python scripts, and we can script like a significant amount of the workflow. But scripts are dangerous as well because, like, can the script survive? Like, if the person leaves, like, if you need to pay someone to come back after he's left the company to update like a script, is that really what success looks like? So probably not. So and maybe to give you like a personal example, like back in 2021, we developed a model. It was like a new acquired mine, loads of like visible gold and complex kind of complex behavior of the grades. And we developed a model that was using disjunctive kriging. It was a top cut model from Jacques Rivoirard, for the ones who know. But it's a very elegant system. You estimate your background grades, and then you have like an indicator that points at the excess of grade. And then you can just resprinkle all your excess of ounces into the right locations without smearing. It's quite an elegant workflow. However, there were like 2 or 3 people who could run the model, but then that number decreased even further if you need to calibrate that model. And if the person who can calibrate the model goes to ski over the weekend and breaks his leg or her leg, that's a problem, because all of a sudden no one can calibrate that model again. So it's a danger, and especially in like in production, loads of tons being moved every day. You don't want to be like hanging over the even if people are very skilled, you don't want to hang over the skills of that individual that knows it all. So it's we stepped back, and we tried some additional ways to model that ore body. And eventually we found something that was a bit more transparent and much easier to do, and getting the same like performance of the model. So you get the same performance. Everyone knows it, like everyone, like you have far more people who can understand and run the model, calibrate the model. Like it's much more transparent. You have pictures showing what's happening inside your system. And we decided to simplify, so to step back from that more complex, technically speaking, more complex model to something simpler, but that was more sustainable. And let me, on the complexity of the models and the way we tend sometimes to get stuck, let me give you a few more examples. Like this is a model I came across recently, and the model has like 245 estimation domains, 5 block size, and 3 passes per block. So for the guys who are capable who can calculate quite quickly in the head, that's 3,675 different ellipsoids being used to inform the model. That's not what success looks like. It should be a warning in your head thinking, well, like, can I maintain that over time? How do I peer review this? How do I check that I haven't done any mistakes while doing that model? And 3,000 lines or 3,000 ellipsoids, it seems like a bit over the top, right? It's a complex geology, we can give it that, but it doesn't mean that it probably can be like reduced. There are other examples like that where sometimes I've seen models where people were running like 40 realizations of conditional simulations and then just aggregating all of them into an E-type. That's what a Kriged model looks like. It's very close to what a Kriged model would look like. So instead of having like one step, you then have like 12 steps for the same outcome. That's, again, it's like, yeah, do we want to do that? I've seen as well, like some people using MIK or LIK, different like, models, and there is not that much variance to deal with. So you creating loads of steps to something that can probably be averaged quite quickly. We can also talk about like, applying some LUC or, LIK would be the same in this regard. But let's say with like little discussion about the localization algorithm, this is just a picture showing like, what a localization algorithm can do. And it's quite, it looks cool. I don't know if it looks true though. I don't know if I would like, if I have like a 200 million capital to invest on a mine to understand, like, you know, where I need to put my capital and my decline and my shaft, I don't know if I would go for that specific model. And it's that there is other examples where you know I've seen people using like conditional simulations, so loads of equations, like billions of runs. Like you need to have something quite, this is, you know, computationally intensive, and using conditional simulations to define like some drill hole spacing. So it's simulations on simulations, and they did that on a trimodal population, no regard to stationarity. Do you want to do that? It doesn't make any sense. You're just adding complexity. You think you're doing something very smart, but the basics are not there. So it's the what I'm trying to explain there is that I'm not criticizing necessarily the techniques, although the, you know, the people who did that, they were like, you know, they did that in good faith, but it should be somewhere, you know, in the forefront of what we do, that, you know, complex, sometimes we go for something more complex because it flatters our ego, and we want to be like, you know, oh, I'm the only one who understand everything I've done. As like, okay, well, okay, is that good or bad? Well, you know, sometimes we see it, oh, it's good because, you know, it means that I'm smarter than everyone else. But really, like, is it what you want? Is it really like that no one really can get and reproduce what you have done? Is that really like, you know, what success look like? So again, you know, if you know, in a production environment, this is kind of the enemy there. You don't want that. You don't want like have something so complex that no one can replicate it. So there is also, like, from a modeler's point of view, well, you know, it's easy to add just one more exception. Oh yeah, let's create just a, you know, you don't end up with the 245 estimation domains just like that. It's actually, to get there, it's you know, you start with 50, and then there is a new one that pops. Oh, let me add that one. Oh, let me add that one. Oh, let me add that one. Oh, here it turns, so I need to break it in two. And so it's just that, you know, naturally people just like make over time like just something slightly more complex. The and complexity eventually is easy to achieve, because if you think of it, it's like where entropy always wins. Just let something just be there, and at some point, you know, it starts to complexify itself, to move around, and until no one really, like, you know, can map what's going on inside the workflow. So what next? Well, you know, the point I'm trying to make here is that making simple models requires more work. You need to think about it. You need, well, in some fashion, it's an unachievable target. It's a forever like evolving like goal, because it's never as simple as it can be, probably, but it requires some active critical thinking. You want to question what the workflow is. Like, do we need that? Do we need to do that step? Like, we are splitting that and that. Do we need to do that? We need to question what we're doing in order to try to, well, simplify, get the best possible something. Just asking, do we need to do that step? What happens if we don't? Then we just have to try. And sometimes we do need that step, because god damn it, otherwise we are just like, you know, really making a mess. But sometimes, and that's my experience, most of the time we don't need to. It's just like we build our mental barrier. We name every single like veinlet, we give it a name, and then, well, you need to administrate that naming. So it's, you can reduce and remove some of the stuff. You can aggregate. You can, at least we should try to maintain things as light and agile and, you know, manageable and sustainable as possible. I talked about it, but, you know, the simplicity would be a corollary to the sustainable model over time. I need to think that that model needs to live for the next 20 years. So we need to find, like, there might be 12 people that will take over that model over the next 20 years. So what would make that process possible, right? So how many people can run the model? I brushed through that. And how many people can own and understand the workflow? That's a big question to ask as well. How many people can explain in 2 minutes how the model is made? one of the things that we're trying to achieve with like all that being said, one of the things that we focus on for that, we focus on some of old-fashioned stationarity. So instead of looking for like more mathematics, we want to get like the right geological context, the right directions. And when we start to estimate something in space, you want to look at histograms. You want to understand, do I like capture things that are reasonably the same well enough? Because, and that's an interesting bit, because resource geos are precious and they are arrogant. And sometimes we think, okay, you know, we need to do loads of math, but to do, oh, you know, resource model, that's complicated. But if you think of it, like a resource model is just like a 3D weighted average. We are just making like some local estimates. We're using some, and sometimes we add some like fluff around it, but eventually we're just doing averages, right? So if you want to do the right averages, you want to have something that is reasonably stationary. In the gold environment, copper is a bit more well behaved in that regard, but in gold, we are dealing with loads of orders of magnitude. So we need to deal with that. And it's the good way is to try to have like different, to have the grades that are similar enough to be able to be averaged easily. You want to look at contact plots, like what is the relationship between these different domains. And if there is no contact, then they should probably be the same thing, same histogram, no contact, you want to aggregate. So I know in academia, everyone is usually rewarded for splitting. So you want to see, you know, if you can find something that is different than the rest, then you can write a master or PhD on it. But in this process here, we need at some point to re-aggregate and to regroup as much as we can to make the final product as simple as possible. You want to look at the like asymmetric border effect. You want to look at how your grades fly in space, and would the high grades or the low grades, you know, move the same way? Would they, you know, can you expect what is the 3D, the spatial life expectancy of a grade? Can it exist for like 2 meters, 5 meters, 12 meters, 100 meters, 2 kilometers? Okay, we want to consider as well, is the model sitting well on the data? And you want to understand like what's your data to model relationship. And one aspect, and obviously that's not, you know, within the industry, like sometimes you don't have that, but in production environment, this is kind of cool because we do. You can just check what comes out of your plant. You know, it's the ultimate kind of like judge of what's happening is you know, like how much like gold bars you're producing, and then you can check and like verify what would different scenarios of your model could how they're faring against that measurement. So if it's not good enough, then you can add some complexity, but sometimes you can also remove some complexity and see if it changes anything. And if the picture doesn't change, then maybe you should remove that complexity. So an achievable quest, but it's a process. So it's something, it's a way of thinking. It's a way of discussing about models. Do we need that? Do we need to do that complicated, convoluted, like backflip in order to get to land here? Or can we just like step in and do that another way? All right, let's finish this thing. Probably, what time is it? Yes, I'm over time. Okay. This one is Tufte. I like Tufte. He wrote a book. This is the name of his book. It's about above all else, show the data. So if we talk here about Antarctica, we have different ways to, you know, we can picture it in different ways. First, it's covered in snow and ice. So that's one way to look at it. If we look at the bottom picture here, we can see as well, this is like the temperatures. So it's cold. And if we look at it there, like we can see as well, like, well, all around it, it's kind of windy, right? So that's different ways to talk about Antarctica. However, if we talk about Antarctica and we want to talk about penguins, well, then we need a picture about the penguin. We need a picture of the penguin. We need to find the right image that is actually supporting, like, if we want to talk about penguins, and I'm looking at a map of Antarctica, that doesn't help me. What I need to find is the actual picture of the penguin. So we need to find the penguin. And if we, so the analogy there with for us is that, well, within my career, I've been on many, looked at many models and discussed with many people. And sometimes people have like these kind of concepts and say, well, there is a strong correlation between that element and that element. Like, okay. And do you have a picture for that? And usually, like sometimes we're no, I think I've read it. It was like someone like back in the day said that, there is a strong relationship between this and that. And then you plot the actual relationship, and the relationship is sometimes true and sometimes not. So you want to back the concept and the mental image we have of a deposit. All the, sometimes we create that kind of thinking that, it goes that way. Well, prove it. Find the right picture. Find the pictures that will support the claim that this is the way it goes. And it's something where sometimes when we are using software, we are doing we have plenty of tools at our disposal to to do things, but we should definitely like try our best to get like the best picture of our penguin. If we have something that demonstrates something very well, then we should invest in that like graph or image or picture or view, because that will support the decisions that we are making down the road. So a few examples of those. If you want to find a penguin, well, ternary diagram can be a penguin if it illustrates that this specific whatever magma rock somewhere is slightly different than something else, and it has like, if it's really core to what you want to model, then that could be a penguin. Or it could be this one, which is just the reduction of the variance as you change the support. And if you move from a point support to like a larger block support, the variance will reduce, and the population will center around the mean. And that could be a good penguin if that's what you're dealing with in some aspect of what you're modeling. It could be a probability plot, like capturing like the crazies, the outliers. It could be like a good contact plot showing like the way the why justifies why you needed to use the soft boundaries for 10 meters between several domains. It can be like I've talked about that one before, but let's say like it could be asymmetric border effect, and the measurement of how the grades can, like what is the range of the different grades as we go up in the grades, and that will like inform decisions that on how you're letting these grades run in the future. It can be histograms. People don't look at histograms often enough. You can get loads of information from a good histogram, put some colors on that so that you have like something obvious to look at. It can be as well just to display your ore body and see how it dances in the ground, and see how it fits. It could be explaining why all of a sudden you want to spend another $1 million to drill some place. Like, find the pictures that illustrate what you want to achieve. It could be the relationship of, well, like a good correlation between different things. It could be displaying your data collected over production over time. Chronostatistics are seldom used, but it's actually a very, very powerful tool. Display independent measurements as they are, which is independent measurements. Look at trends. It could be a good nomograms with some colors and something that explain why this sample is better than this one. It could be like displaying finding the right color code for the different for the variable that you want to display or you want to consider. It could be looking at like maximum intensity views so that you can understand what connects with what. So find your penguin, invest in the pictures, invest in the color codes, think about it, think on what could highlight the best the ID that you have, and that supports the decisions that you're making the best. And it's well, I'm passionate obviously about like color codes and all these things and these pictures, but I do think that it helps if I need to explain to someone what happens in the model, and you have like one cool picture that shows what's happening, then your explanation can, like, it's one slide, one picture. You don't need like 200 pages report to explain that, well, this is what's going on. Have a look. Look, we have a picture, we have a penguin. The last one, and I will be done. Sorry, Jessica, I'm running late. This one, oh, Groover. So that's the name of his book, actually. Groover was an Intel CEO, and I like it. Like, only the paranoid survive. That's that's cool. So just to bit of context, like, I remember back in 1992 when they released the Pentium. There was Intel inside, and that was kind of like the new stuff. Like, wow, the microprocessor from Intel was in, and it's quite fun because 30 years down the road, I still have like a laptop today that is actually has like a Intel microchip. So the Intel actually conceptualized, and that's what is in the book of Groover here, as it conceptualized the idea that people are, they were actually quite paranoid, and especially in the IT, well, computer science environment, things are moving quite fast. So they wanted to stay, on top, and they had to be kind of very agile and very, like, thoughtful of what they were doing in order to stay alive. The analogy for us in resource modeling is that, well, you can phrase it that way, like, there are some consultants that are actually paid like $2,000 a day to check a model or to look at a model, to do a model. The reason you pay them that money is because, well, they double check, they triple check, they have an army of people checking, and actually the whole industry of consultancies, people checking stuff. Like, they will check the data, look at the data, and check. So the same way we're talking about, like, finding penguins and finding the right image, the on checking the data, displaying the data, and going through that thoroughly is the essence of the work. It's sometimes like not very fancy and not very sexy, but it is the essence of the work. We don't assume, we just look at it, like find the metric, look at the data, find the metric that can tell you what is inside. Sometimes it's just counting the drill holes and data types, and sometimes it will be looking at other stuff, averages and other metrics. But we need to find metrics to, like, look, check, what is that data doing against that one, what is the QQ put between this and that, like, how does it behave, and yeah. So that was these were my slides for today. I'm trying to share a bit of the, so we share these kind of slides with people who are just entering the world of resource, so that it sticks with them. So it stays when you're doing later, if you're doing a model and you're all of a sudden like, oh yeah, cool, let's do that fancy, like, instead of having one mod domain, I can have like 21. It should like pop some sort of like warning light somewhere in the back of the head, thinking, do I need to do that? And yeah. So that was it for me, Jessica. And that's the end of it.
That was brilliant. Thank you so much. Yeah, that was really cool. I could have kept listening for much, much longer. So thank you so much for doing that.